So your test will be on Thursday because Friday classes are a little bit shorter. So unless you plan on writing really fast, sorry. Friday's probably not a good choice. Am I correct? So it's got to be Thursday, yes. Yeah? Okay. So hopefully we're going to finish up most everything today and then maybe just have a little bit tomorrow and then just like Tuesday, Wednesday, whatever time we're not learning something new, we're going to review. Is good? Okay. Hopefully you did a little review over the weekend. Okay. There we go. All right. How did we do with the homework with the electrolysis? Anyone got any questions on any of that? Why does water do that? Because water is capable of accepting electrons and giving electrons just like any other species. Like, why do the other ones do it? Oh, the overpotential effect. The overpotential effect is just weird and I don't understand it. And neither do really, like I've looked up numerous explanations and none of them have been satisfactory to me. I think it's just because real life gets in the way. You know what I mean? It's like due to real life, not theoretical life. Yes. You will never say, for example, use 1.37 or 1.38 for water. Water either wins because it's the best, or if you're comparing it with, say, bromide, which is probably one of the only, or chloride, usually the rest of them in here don't get mentioned because they're complicated. Do you know what I mean? But bromide and chloride are kind of the ones that you might do. Maybe this one here, maybe that one there, but I really think it's really bromide and chloride. They will win, quote unquote. They're preferentially oxidized over water. Now, do you have to care about the overpotential effect on the AP exam? No. Okay, overpotential effect does not occur on the AP exam. They won't bother with it. So that's kind of nice. All right. And quite frankly, I think on the regular exam, you can mostly ignore it as well. Okay. It's like it might show up once in a blue moon, or you can just be like, I'm going to play the odds and not worry about it too much. You know, I think when I was in high school, I do remember playing the odds on the equations for acid rain and corrosion. I'm like, close enough. You know, I had other fish to fry, had like, 4 government exams at the same time. I'm like, that's okay. Yeah, so. Any other questions? Yes. Do you still have to do 3E, yes. Okay, so for 3E, we have K2SO4. So we have K plus, we have SO4 2 minus, and we have water. So let's then go to our data booklet. And so we have SO4 and water. And let's see, do we have SO4 anywhere else? SO4 is also here, but what do you notice about this SO4? It would require acid in order to react. So that one will not occur. Okay, if you don't have acid present, which you don't because it's just potassium sulfate, that reaction cannot occur. So we have that, and we have potassium. Now, if you remember, all of your alkali and alkaline earth are really terrible at getting reduced. So water is always going to win because all of the alkali and alkaline earths are down here at the very bottom. Whoops, even there, right? So we're now looking at water. And we could look at potassium, but it's not going to win because water is reduced preferentially. And then we're looking at water here. And we're looking at sulfate here. Sulfate's not going to get reduced. So what we've got then is we've got water being oxidized and water being reduced, which is definitely a possibility. It's just the electrolysis of water. You're going to end up with hydrogen and oxygen as your products. So we would have, let's write down those two reactions, the two half reactions. We have H2O. Oh, maybe my battery is not happy. Let's see. We have H2O. Goes to 1/2 O2 plus 2H plus 10 to the minus 7 molar plus 2E minus. And that, the E naught for that oxidation is, I'm going to change the sign that's on the table, negative 0.82 volts. And then we have the reduction of water, 2H2O plus 2 electrons goes to H2 plus 2OH minus 10 to the negative 7 molar. Now this 10 to the negative 7 molar doesn't mean that that's the concentration that we are making. What it means is we're starting out in neutral conditions. So our initial cell voltage is based on the fact that this thing is neutral to start with. But every time we make 2 H's, we also make 2 OH's. So when we actually add this up, these two are going to get together to form 2 waters. Yes? So that, I think, is maybe the trickiest bit. The 2 electrons cancel with the 2 electrons, so we don't have to multiply either of the equations. And what we are left with then is 3H2O, because we got a 1 and a 2. And then we go to 1/2 O2. I haven't left room for the hydrogen, so I'll put it over here, H2. And I look and I'm like, oh, look, I got 2 waters over here and 3 waters over here. So that's going to leave me with 1 water there. The reduction of water is negative 0.41. And so the E naught cell is 1.23, negative 1.23 volts. Is that good? Cool. Other questions? Alrighty. Good stuff. All right. So we are going to look at electroplating today. Electroplating and electrorefining. Not there. Where's electroplating? Oh, we got a video of it. Yeah, that's right. I didn't actually make a handout on this because I ran out of time. And quite frankly, it is in Hebden. So if you want something printed out, you're going to use Hebden. Don't worry about going to a page here. I'm just trying to find, there we go. Now, do you guys feel like Mr. Colger or Tyler? Tyler? Okay. Huh, okay. Okay, Tyler, electroplating. Did I not put the, oh, I didn't put the link there. That's okay. He'll be easy to Google. Tyler DeWitt, electroplating. There we go.
In this video, we're going to talk.
And here we go. Let's make that big. Shall we watch him fast? Maybe 1.25 fast? Okay. You can tell me if you want me to change the speed later. We aren't. I didn't make a handout for this because 40 pages is about all I can manage in a week. So we're just going to watch this, and then if you want to read about it, Hebden has some reading on it. So, okay? Yeah. And I'll give you the page references for that.
Talk about the chemistry of electroplating, which is a really common technique used for metals. And it just happens to be one of my favorite topics in all of chemistry. So in simple terms, I'd say that electroplating is a process where you usually take an object made of one type of metal and you cover it with a thin layer of another type of metal. Okay? And let me tell you, electroplating is often just called plating for short. Okay, so electroplating or plating is used for many purposes, but one of the most common uses is to make inexpensive jewelry. If you see something like a gold necklace or a silver ring and it's selling for real cheap, it was probably electroplated. Pieces of jewelry like these aren't made of solid gold or solid silver. Instead, they're made of a cheap metal like copper or zinc, and then electroplating is used to put a thin coating of gold or silver onto the surface. That's how the jewelry can be so cheap, because it's mostly made of an inexpensive metal, and you only need a tiny amount of the really expensive precious metal to just coat the surface of that cheap metal. So let's talk through the chemistry of electroplating. Let's say we have a copper ring and we want to plate it with a thin silver coating. Here's how we do it. So we'd start with a copper ring and a piece of solid silver.
Now, I actually want you to think, if we want to plate that copper ring in silver, what would we need to have in our beaker? Aqueous silver, aqueous Ag+, yes? Because the Ag+ is going to have to turn into AgS. What process is that? That is reduction. So what does that mean? The copper ring has to be the what? Which electrode? Has to be the cathode, because you want silver to get reduced from silver plus to silver 0 on the cathode. Okay? So whatever you're wanting to electroplate is always going to be the cathode, because you want the reduction of the metal ion to silver. Now, you've got silver in the solution. Eventually, though, what's going to happen to the silver in the solution? What's going to happen to its concentration? It's going to go down. Wouldn't it be nice if we could keep it from going down? Wouldn't that be nice? If we could maintain a higher concentration of silver, make the reaction more efficient? How could we do that? Tell your partner. How could we make more silver ions to replace those that are getting plated onto the copper? How can we make more silver ions? Okay, are we good? What do we think? Where are the silver ions going to come from? From the piece of silver. And in order for silver to turn into silver ions, Ag+, what do they have to do? They have to be oxidized. So that would make silver the anode. And so you actually have silver being oxidized at the anode. What's happening at the cathode? Silver is being reduced. So what's the voltage going to have to be to run this cell? Well, the oxidation of silver and the reduction of silver, I don't know if I'm doing that the right way. You've got one going one way and one going the other way. What is the reduction potential compared with the oxidation potential? How do they relate to one another? They are the same, just different signs. So if you add those two up, what voltage will you get? 0. So the cell potential is 0. So basically, if you just turn on your power supply to anything bigger than 0, that cell will run. Okay? Now let's watch Tyler walk us through this. So if any of that just went over your head, Tyler will make it better.
What we want to do is we want to get some of the silver atoms to come off this piece of silver and transfer them over onto the surface of this copper ring. So the first thing we're going to do is put these two objects in liquid. Here's a liquid. Now this liquid is water with some chemicals dissolved in it. We'll talk more about it later, but for now I'm just going to call this liquid the solution. But just putting the silver and the copper ring in the solution isn't enough to start the plating process. And that's because electroplating is a type of electrolysis, which means that we have to use electricity to cause a chemical change. Here, the chemical change is putting some silver atoms on the surface of this copper ring. So here's what we're going to do. We'll pull out some wires and hook these two objects up to a battery. These are the wires, there's a battery. Now check out which side of the battery these objects are connected to, and that's important. We hook the silver piece up to the positive.
What would happen if you flipped the battery? Yeah, you'd end up with copper plated onto the silver, which is not what you wanted. So there you go.
Side of the battery, which means that the battery is going to be trying to pull electrons out of the silver. And electrons are going to be moving through the wire in this direction towards the battery. And then the copper here is going to be connected to the negative side of the battery, which means that the electrons are going to be moving out of the battery into the copper ring. They'll be moving along the wire in this direction. So that's our setup, and we can call this an electroplating cell, which just means a device that you use for electroplating. So that's the big picture of the electroplating cell. Now I want to talk about how this actually works, right? How we can get silver atoms off this piece of silver and transfer them onto the surface of the copper ring.
Now, do we want to see this? Yes? Good.
In order to understand that, we got to use our atomic vision to zoom in millions and millions of times so we can see the atoms and the electrons that make up the silver piece, that make up the copper ring, and that make up the solution. So here is a magnified view of the piece of silver and the copper ring. These circles here are the atoms. Ag is the chemical symbol for silver, and Cu is the chemical symbol for copper. And these sections here are right on the edge of the pieces of metal. So here, for this silver piece, I'm imagining that this magnified section is right here. So everything to the left is the piece of silver, but then everything to the right is the solution. Now, these two objects are way closer in my magnified view than they are in real life, but I want to make sure that we can see both of them. And then over here on the copper ring, I'm magnifying this section right here on the left side, so everything going here onto the right is in the ring, and everything on the left is in the solution. Okay, so remember what our goal here is. We want to move some of the atoms from the piece of silver onto the surface of the copper ring. How are we going to do this? Well, here's how. We're going to move them by changing their charge, okay? This is one of the most important rules in electrochemistry, that neutral atoms make up solid metal. And you can see that all of these atoms here are neutral. They're just Ag. They don't have a charge. But on the other hand, metal ions can usually dissolve in water, okay? So if we can change the charge of these neutral silver atoms, and if we can turn them into ions, we can get them to dissolve off the piece of solid silver and move into the solution, all right? That is the job of the battery. That's why we've hooked it up to the battery, okay? Remember that there's this wire at the top of the piece of silver leading to the positive side of the battery, which means that electrons are being pulled to the battery in this direction. So here's what's going to happen. I'll take this silver atom as an example, okay? what's going to happen is one of its electrons is going to get pulled out by the battery, okay? And so it's going to move through the metal up in this direction to the battery. This silver atom lost one of its electrons, so that means that it's now going to have a positive charge. It used to be neutral Ag, but now it's Ag1+. So now it's an ion, and it's no longer going to be part of this solid metal. Instead, it's going to float away from the solid piece of silver and move into the solution. And this is all because we changed the charge. We changed it from neutral to +1. Let's see that happen again. We'll take this guy, pull out one of the electrons. This electron moves up to the battery. Since this atom just lost one of its electrons, it's now going to become Ag1+, and it's going to move out into solution, coming away from the solid piece of silver. This silver atom right here loses one of its electrons up to the battery, and it becomes another Ag1+. Okay? So now we have these 3 silver ions that have entered the solution, and they've come apart from the piece of metal. Now, sometimes in drawings of electrochemical cells like this, people will actually change the shape of the silver to show that pieces of it are coming off. So I'll actually do that here, just in case you run into a diagram like this in your textbook. See, what I've done is I've made the edges jagged instead of smooth to show that chunks of the silver are actually coming off as the atoms get turned into ions. Okay, so now we have ions that are dissolved into solution that have come off the piece of silver. Now the next thing I want to do is I want to get them stuck to the surface of this copper ring here. So how am I going to do that? Well, we're going to do the same thing that we did here. We're going to change their charge, okay? Keep this rule in mind. Neutral atoms make up solid metal. Metal ions can usually dissolve in water. So right now, these dissolved silver ions are floating around, but if we could turn them back into neutral atoms over here, we could get them to start making solid silver on the surface of the copper ring. Now, what are we going to have to do to change these from Ag+ into Ag neutral?
What are we going to have to do? Give them an electron.
Well, since I have a positive charge, we'll need to add 1 electron to each of them. And that is what this battery is for. Remember, the battery is trying to pump electrons down into the copper ring. So here's this here. Electrons are being pushed from the battery down in this direction. Let me just move this over here a little bit. There we go. Electrons are being pushed into the copper from the battery. So let's look at what would happen, okay? Here comes an electron down from the battery through the copper. Now this electron is negative, and the silver ions are positive, so they're going to begin to attract. And this electron is going to go into the silver, and now the silver has gained an electron, so it no longer is positively charged, and it turns into neutral silver, and it sticks to the surface of the copper ring. It starts to form solid silver, right? It's no longer dissolved in water. It's gone from 1+ to neutral, so it's now solid silver, okay? The same thing is going to happen with another one of these electrons. It comes down from the battery into the copper. It goes into the silver ion. The silver ion loses its charge because it's gained an electron, and bam, it's neutral silver, and it's turned into solid silver on the surface of the copper. One more, because I just think this is so cool. 1 more electron down from the battery, shoop, into the silver ion, turns it into a neutral silver atom, and as you can see, we're building this surface, this very thin surface or coating of solid silver on the outside of the copper ring. So sometimes, if I were drawing this in a diagram, I might show this with something like this to indicate that the copper ring looks like it's turning into silver. It's just getting this layer of silver atoms on the top of it. Okay, so that's the piece of silver, and that's the copper ring. The last thing that I want to talk about is the solution, okay? Now, this electroplating process won't just happen in regular, pure water. You've got to dissolve some chemicals into the water to allow electroplating to happen. And if you're electroplating silver, a really common chemical to dissolve is called silver nitrate. That's what you dissolve in the water to make the solution.
And why are we choosing silver nitrate above some other silver compound? Nitrate, it's soluble with everything, plus it is very electrically unreactive as well. Okay, so it's not going to undergo electrolysis.
Now, silver nitrate is an ionic compound. It's made of 2 things. It's made of Ag1+, and it's made of the nitrate polyatomic ion. 1+, 1-. And when silver nitrate dissolves in water, the Ag1+ and the NO3 1- come apart. Okay, here's another one. They'd be stuck together, and then they come apart, just like this. So by dissolving the silver nitrate into water to make the solution, we get these positively and negatively charged ions floating around here. These ions have a number of jobs, okay? First, you can imagine that adding more Ag+ is a good thing because these can then move over here and turn into solid silver on the surface of the copper ring. The negative nitrate ions are important because their negative charge balances.
And what are they going to do? They're going to provide charge balance. Yeah, so as the solution around the anode becomes more positive, because the silver ions are coming off, the nitrates are going to move in there to balance out the charge.
Balances out the positive charge of the silver ions that are coming into the solution from the piece of silver, and we always want charges to balance, okay? But the most important job of the positive and negative ions is that they act as electrolytes, which means that they allow electricity to flow through this solution. They complete the circuit and they allow the battery to work. Okay, so the battery can then pull electrons here and push them into here. Okay, so that's why the solution is important, but I don't want you to worry too much about it. All I want you to keep in mind is it's just important to dissolve an ionic compound in water in order to make a solution. That electroplating isn't going to happen in just pure water. So now that we've talked about the silver, the solution, and the copper ring, let's just look at this whole process one more time, okay? We go over here to the piece of silver. One of its electrons is pulled out by the battery, okay? This turns it from a neutral silver atom into a silver ion. It floats out here into solution, and then it comes over here to the copper ring, where an electron is moving down from the battery. The electron goes into that silver 1+ ion. The silver loses its charge and becomes solid, neutral silver on the surface here of the copper ring. Okay, so now that we've looked at how this process of electroplating works, I want to talk a little bit more about how we can describe this using terms of oxidation, reduction, anodes, and cathodes. So let's take a look at that.
So do we want to watch part 2? Yes? Yes. Ooh, you know what? You could probably actually calculate that, because you would calculate like how much mass you want to plate on, and we're actually going to go into those calculations in the AP stuff. So you'll end up using coulombs per second, so the amount of current, coulombs per second, and then there's like Faradays in there too. I can't remember why we use Faradays, because I only teach this once every 2 years. I'll remember when we get there. Yeah. I honestly don't know exactly how long it takes. Yeah. Sure, we could try. Let's see if there's a time lapse. Okay. Time lapse electroplating.
So in the last video, I got a number of comments from folks who said they wanted a time lapse of the electrorefining process. So those of you who missed the last video might be a little confused at this point. Why is this man dipping a resin flamingo into a blue bath? Does that flamingo owe him money? Is that flamingo in danger? Yes, is the answer to both questions. If you missed the last video, this would be a confusing process. It is all about electroforming. I'm going to be turning a resin flamingo into a beautiful copper steampunk version of itself. And hopefully, you'll get to watch along with me. We apply electricity to this circuit that we made, and copper flows from the anode and the solution onto this flamingo. It's hard to see through this liquid, but what happens with the copper is it gets really bright. Presumably, we'll start seeing a bright section here. And you can see the copper wire coming down here from the top. This is the rubber piece that's holding the weight, and the flamingo is actually floating out in this direction because it is just too light for anything else. So the copper should start from this point here where the wire is touching it, and we should see it form all the way down to its feet from there. There we go. I'm going to go ahead and rinse the solution off of it, and we can take a closer look at it. Nice little copper coating on there. You can see there's a tiny little bit of conductive paint there under the beak and by the leg, but the rest of it coated really well. So if we left it in here,
I was wondering how they got the flamingo to actually like coat, because it's plastic and plastic does not conduct electricity, but they said they had a conductive paint that they put on it first, so that made sense. I was like, how are they doing the plastic? I don't get it. But anyway, so there you go. All right, and now we will go back to Tyler and look at cathodes and anodes and all those kinds of things. Electroplating part 2. Woo! Okay.
Over here on the copper ring, a silver 1+. In the second part of this video, we'll talk about some more of the details of electroplating. We'll write chemical equations for the processes that are happening here, and we'll talk about oxidation and reduction, anodes, and cathodes.
Oh, it is.
In the previous video, I showed the electroplating process by moving a bunch of papers around, sort of animating it. Here, I'm going to be using a diagram that doesn't move, that's a lot more like what you'd see in a textbook or on a worksheet. So this is what I'm trying to show. Here, a neutral silver atom loses one of its electrons that's pulled towards the battery. This turns the neutral silver atom into a silver 1+ ion, and it comes off the surface of the metal, dissolving in the solution. Over here on the copper ring, a silver 1+ ion gains an electron. This ion loses its charge and turns into a neutral silver atom. This neutral silver atom can no longer dissolve in the solution, and it now forms solid silver as it sticks to the surface of the ring. So that's how you show the process using a diagram. Now let's see how we could describe the same process by writing chemical equations. We'll start with what's happening over here on the copper ring. So here we start with the Ag 1+ ion. And now what's the physical state of the Ag 1+? Well, it's dissolved in a solution. So I can show that by writing Aq in parentheses after it. Aq stands for aqueous, which means dissolved in solution, dissolved in water. So Ag 1+ then receives an electron. So I will write plus E-, the symbol for electron. And then I got my arrow, and what does this give us? It gives us a neutral silver atom, Ag. Ag, we know it's neutral because there's no charge up here. If there's no charge, it just means it's neutral. What is the physical state of this atom? It's solid. Solid metal sticking to the surface of the copper ring, so I will indicate that with an S in parentheses. So this is the equation for what's happening here. Now the equation for what's happening on a piece of silver is a little bit trickier. So I'm actually going to start out by writing it incorrectly because I think that makes more sense, and then I'll show you how to fix it. Okay, so on the piece of silver, we start with neutral Ag. Okay, so a neutral Ag atom, what's its physical state? It's solid. It's part of the solid piece of silver. Okay, so there's an S. Now, what happens, and this is the part that I'm going to do incorrectly, is this Ag loses one of its electrons. So I'm going to write minus E-. That's not right. We'll fix it in a minute. And losing that electron gives us Ag1+ that is now dissolved in solution, so it's going to be Aq. Now, what's wrong with this equation? Well, it's this minus sign right here, this minus E minus. Because in chemical equations, you can't subtract things. You can only add them. So I can't put a minus sign in front of this electron. Well, then how do I show that this Ag is losing an electron if I can't use a minus sign? Well, what I do is I move the electron to the other side of the equation, just like you do in a math problem, and this will change its sign from negative to positive. Let me show you what I mean by rewriting this. Okay, so we got Ag, solid, and then I'm going to be moving this electron over here, so I'm just going to put my arrow. Now I have Ag1 plus, that's aqueous, and now that the electron is going to be on this side, I change its sign from minus to plus, plus E minus, and this is the correct way to write the equation for this process. Putting the E minus over here shows that it's no longer part of the Ag here. Okay, so it's like putting it here shows that it's now coming apart, that it's not part of it anymore. Okay, so these are the two equations for what's happening here. Now, you can look at the diagrams, or you can look at the equations here, and you can definitely tell that there's transfer of electrons going on, okay? So this is definitely an oxidation-reduction process, okay, because there's transfer of electrons. Now, I want to talk about what's going on here in terms of oxidation and reduction, okay? So just to refresh your memory, reduction is electron gain, and oxidation is electron loss. So what's happening over here on the piece of silver? Well, we have these neutral silver atoms that are losing electrons, turning into ions. So, loss of electrons over here on the piece of silver, oxidation is taking place. Over here on the copper ring, these silver ions are gaining electrons, so reduction is happening here, oxidation and reduction. Now, both of these equations that we wrote are actually called half reactions, because each one of them tells us half the story of the oxidation-reduction process, right? Here's the oxidation part, here's the reduction part. Put them together, we get oxidation-reduction. So finally, there's one more thing I want to do. We can give names to these parts of the electroplating device based on whether oxidation or reduction is happening there. Okay, these are the two names that we're going to be using, cathode and anode. The cathode is the site of reduction. It's where reduction happens. And the anode is the site of oxidation. It's where oxidation happens. So over here on the piece of silver, these neutral silver atoms are losing electrons. Oxidation is taking place. So the piece of silver is the anode, the site of oxidation. Over here, these Ag1 plus ions are gaining electrons. Reduction is taking place. So the copper ring is the cathode. Anode, site of oxidation. Cathode, site of reduction. So that's everything about electroplating. Let's just tie this information all together with a big picture. Here's our electroplating cell. We got a piece of silver, a battery, and a copper ring. On the piece of silver, neutral silver atoms are losing electrons. So oxidation is happening, and we can call the piece of silver the anode. Losing electrons turns the neutral solid silver into silver 1 plus ions, which means that they come off the surface of the piece of silver, they dissolve in the solution. Then over here on the copper ring, these Ag1 plus, the silver ions, get electrons added to them. They gain electrons. So the copper ring is where reduction, gain of electrons is happening, and we can call it the cathode, the site of reduction. Gaining those electrons turns the Ag1 plus ions that are dissolved in the solution, it turns them into solid silver metal, so they form a layer of solid silver on the copper ring. So just remember, the next time you see a piece of gold or silver or platinum jewelry for sale for really cheap, chances are it is not solid precious metal all the way through, but it's been electroplated, just like this.
Okay, so that is electroplating, and what we're going to do is, so you have a page reference for this. This is on the electroplating, this is on like the electrolysis videos page. We're also going to
talk about
no.
electrochemistry. We're going to focus on how the voltaic cell works. We're also going to...
The organic chem tutor, he's awesome. Okay, so where it says electroplating, number 9, okay, we're going to write down Hebden, or you can write it anywhere you want to. You can put it on your front cover of your book, actually, if you want to. That might be a good place for it. Electroplating is Hebden. Pages 243 to 244. So if you're looking to read what's happening, if you want a little written explanation, it's there. There are also some exercises. Okay, so you can either put it in here or you can write it on your front cover of your book. That's also a good place. We're also going to be taking a look today at electrorefining, and this is in Hebden on page 245 to 246. Okay. So, shall we watch the electrorefining video? Okay. And you can see they also have an electroplating video, and that's on your list of videos. So if you should want a quicker review of it, it is there as well. Ooh, slow today. Oh my God. Is it? Okay, it is doing something.
Cathode must be a pure sample of the metal we want to refine. Remember, the cathode is attached to the negative terminal.
Come on. Oh.
No, sorry, I'm sitting with really bad.
Oh my God. Okay.
In many applications, a very pure form of a specific
Well, this might. I mean, I can just do it. Like
metal is required.
It's
One
nice to have
method
the
used to
animations,
purify
though.
metal is called electrorefining. It uses a type 3 electrolytic cell. The most important thing to know for electrorefining is the anode is an impure sample of the metal we want to refine. Remember, the anode is connected to the positive terminal of the power supply. And the cathode must be a pure sample of the metal we want to refine. Remember, the cathode is attached to the negative terminal. In this video, we'll use the electrorefining of copper as an example. On the impure anode, we'll represent.
Okay. So yeah, it's having issues, which is why it's fuzzy. Okay. So we're just gonna have a little chat here. So here on the left-hand side, sometimes they call this pig copper. I don't know why pig copper, like P-I-G, like a pig. Okay. Anyway, over here, what we've got copper atoms, but within the copper, there is also some gold, there is some zinc, and perhaps some lead. Now, while we let this thing think for a moment, we're going to go to our data pages, and we're going to look up copper and gold and zinc. Let's just go look up copper and gold and zinc metals. So make sure you have your data booklet out. Go look up copper, gold, and zinc.
That's why my wife has on me.
All right, there's our copper, there's our zinc, and there is our gold. Who is the best at getting oxidized? Zinc. So that will help us get zinc out of the unrefined copper. Yes, we've got zinc in there. You can see those are the sort of silvery ones. So the moment that you turn this on, this zinc is going to turn into zinc 2+. Is that a good thing? Are we getting rid of zinc that we don't want? Yeah. Yes. Okay. Now, who's going to oxidize second? Copper. So once any zinc that's on the outside of the electrode has oxidized, then we're going to be oxidizing the copper. So that'll take up most of the rest of it. And gold is basically what's going to happen by the time all the copper is gone. What's going to happen to these little gold atoms here and here? They'll be alone, and what will they do? They'll just fall to the bottom because they're not attached to much of anything anymore, yes? So you're going to have like pure gold, like just falling to the bottom. So the zinc has come out as ions. The gold is just going to stay as gold atoms, gold 0, and the copper has turned into copper 2+. Now, we would like this copper that has turned into copper 2+ to become pure copper. How can we get it to turn from copper 2+ into pure copper solid, copper 0? We can reduce it at the cathode. So isn't it nice? We've provided a pure copper as a starter, right? And we're going to then have the copper plate onto the copper. So now you're going to have that starter pure copper and pure copper plating onto the copper. Now, in our solution, if we didn't have any copper 2+ to start with, some of that zinc might come out and then plate onto the copper, and we don't want that, right? So what we're going to do is we're actually going to start with a solution that has copper 2+ in it already, okay? Because if we go and we look at our copper 2+, and our zinc 2+, who is going to be preferentially reduced, copper 2+ or zinc 2+? Copper, because it is better at getting reduced, copper 2+, yes? So what that means is that as long as there is copper 2+ in solution, any zinc that actually does come out into solution will not get reduced, and you won't risk, putting impurities into your now purified copper. So you will actually start with some sort of seed copper 2+. So you might have a copper sulfate solution in order to do that. Let's see if we're actually getting video that we can watch now at this point. Oh.
An assortment of atoms, mainly copper, but with some impurities. And on the pure cathode will represent all copper atoms, as this is pure copper. We'll add some aqueous copper 2 sulfate to the cell. If we're going to purify copper, we must have copper 2+ cations in the electrolyte. Neither water nor sulfate ions will react in this cell, so we'll...
Is this worth watching? It's very fuzzy. Would you like to just watch it on your own at home when it's not so fuzzy? Yeah? Okay. Because I'm just feeling like you can't see anything here. You'd do better off, I don't know what's up with the internet today. It's just a little slow. Okay. So that being said, I think at this point, we could do corrosion tomorrow. It doesn't take very long, okay? And you have lots of work and review, yes? So, let's see. Do you want me to assign anything, or do you want to just pick what you're going to work on? Pick? You just want to pick stuff? Good. That makes my life easier too. So pick something that you want to work on. If you're like, I wanted to review the electroplating today, you can go to the Hebden and do the questions that are in there. If you want to do electrorefining, you can read about that in Hebden. You can watch that video on electrorefining, or you have many, many review packages. So you can work through those.